Okay, so I had somebody ask me a question and they sent me their assignment and they were struggling, so I thought I would help them. And that's what this video is about, particular, is a student's problem. And the question they had was regarding question 1, which said thinking, and then always draw a picture and establish positive coordinate system. This lady is standing on a roof. It's kind of hard to read, but she's standing on, or I guess it's a him, on his roof at home and is 7 meters off the ground. He throws one rock straight up at 5 meters per second, and he waits exactly 0.8 seconds and throws a second rock straight down at 0.6 meters per second. Which rock hits the ground first, and how much sooner did it reach the ground? Okay, so we'll start with just drawing a picture. And honestly, because of the unfortunate quality of my picture, it's going to be helpful. Okay, so let's use this to draw the house. I guess the house can be black. And the man, I guess he'll be a green man. Is standing 7 meters off the ground. Okay. So we have our picture set up. Now we need to define what's positive and what's negative, and in particular where our coordinate origin is. So we have a lot of freedom and we have a lot of different options. What I'm going to do, so the two places where we could put our origin would be right where the man is. You can put the coordinate origin anywhere. Another one is just, oops, that's not where I wanted to put it. I'll hand draw it actually. Is we could draw it so our origin is right on the ground. And I think that makes the most sense to me. Basically right where the man's standing is at the point 0.7. I know you can't see that very well, but we're going to let up be positive and right be positive. Even though there's no rightward horizontal motion, there's only up and down. We're going to let up be positive. And we're going to let the ground right below the man be the origin. That's going to help us with our equations. Okay, so what I would recommend doing is breaking this up stone by stone, or rock by rock. So for rock 1, there's only Y motion. It's just going up and down. So let's look at Y motion. Well, all of our kinematic equations will involve a variation of some of these variables, which is Y initial, Y final. I'm going to use initial there. Y final, V initial, V final, acceleration, and time. Which one of these do we know? Well, we know one of them is going to hit the ground, or well, they're both going to hit the ground. So your Y final is 0. And he's initially throwing it up from where he's at. So your Y initial is 7. Hopefully that makes sense. The rock starts here. He throws it up, it goes down, and it ends up on the ground at 0. The initial velocity, I believe it gives us in the question, 5 meters per second. We don't know the velocity it hits the ground with, but we know the acceleration is going to be g. Now, what we want to do is find, so this is Y motion for the rock. Let's box this. For rock 1, we'll keep it orange. So we need an equation that relates time, because ultimately that's what we're looking for, with all the stuff we know. Well, you can look at your kinematic equations. I think I even derived most of them at the channel, on this channel at some point. And the equation of motion I'm going to use, and probably the most common one you'll end up using, is y final equals y initial plus v naught, this is assumed in the y direction, times time, plus 1/2 gt squared. Well, there's no initial position. That's starting at our origin, right? We're saying, oh, I'm sorry. There's no final, our final position is going to be 0, because that's where we're hitting the ground. So we have 0 equals y initial plus, and I'll go ahead and put numbers in. We have y initial, which is 7, plus v initial in the y direction, which is 5, times time, plus 1/2 gt squared. Okay, well, one thing to keep in mind is this, I'm going to write it, maybe it'll look a little more familiar like this, 1/2 gt squared. I'm just rewriting this a little bit differently, so the powers go in descending order. And keep in mind, 1/2 g is a constant, 5 is a constant, 7 is a constant. So we could try factoring this, but it's going to be incredibly messy. Instead, what I would recommend is doing the quadratic formula to get your t, which, if we remember, is just negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, where this is a, this is b, and this is c. And this gives us our t value that we're looking for. Okay? Well, let's see. Negative b is negative 5 plus or minus the square root of 5 squared, so that's 25, minus 4 times a, which is g, times c, so 28g. Right? So it's, I'm sorry, should be 1/2. So it's 7/2 g. All divided by 2 times 1/2 is just 1. So I don't need to do that. It's just this nicely. I'm sorry, let me fix this real quick. Minus 4 times a times c. There we go. So negative 5 plus or minus the square root of 25 minus 4 times 7 is 28. Half of 28 is 14 times gravity g. Now it's important to note gravity will always be pointing down. Gravity is going to try to pull the rocks and everything down to the ground. So this is gravity. It's always going to point down. When the rock is here, gravity is going to point down. When it's here, it's pointing down. Here, it's pointing down. It always points down. And because we're letting down be negative, g is equal to negative 9.81. But what I'm going to do is I'm going to just take this negative and put it out front and make that positive. Okay, so we have negative 5 plus or minus the square root of 25 plus 14 times gravity. Okay? That's one time. All you have to do is plug this in your calculator and you'll get your time. Now that's the time for rock 1. Rock 2 is a little different. He waits 0.8 seconds and throws the rock straight down at 0.6 meters per second. Okay, so we're going to do something pretty similar. We're going to say, well, now we want rock 2, and rock 2 only has x motion. So we're going to do the same thing we did at first. And we actually know a good chunk of this. So y initial starts at 7, y final is 0. He waits 0 and throws it straight down at 0.6 meters per second. So 0.6 meters per second is our initial velocity. We don't know the velocity it hits the ground with. You know, acceleration is t, and I'm going to call this T2. I'll go up and just make sure we know this is T1. This is for T1, T1, T1. T2 is just T1 plus, or, no, we don't want to do that yet. We'll keep that as just unknown. All right, so we have all this. Let me see if I can box this. There we go. That's the same thing we did with rock 1, except with rock 2. Now what we need to do is we need to find the time that it hits the ground. Well, we can use the same equations before. I'm just going to write it as delta ty, or delta y, sorry. V initial t plus 1/2 gt squared. Or 0 equals y initial, which is 7, plus 0.6 t plus 1/2 gt squared. And this is T2. The time it takes rock 2 to hit the ground. And again, we can follow the same procedure as before, where we just say, well, negative b plus or minus the square root of b squared minus 4 times a times c is equal to T2. So you'll get negative 0.6. So this, make sure we're okay. This is C, this is B, and that is A. Okay? Plus or minus the square root of, let's see, 0.6 squared is 0.36 minus 4 times A, 1/2 G, times C, which is 7, minus 0.6 plus or minus 0.36. Let's see, that's going to be minus 14G. And also, I'm not dividing by, I mean, the equation has 2A, but 2 times, oh, I'm sorry, A is actually 1/2 G. So let me correct myself up here. This should all be over G. There we go. The 1/2 cancels with the 2, but I forgot the G is also part of that. And G will also be a part of this. Sorry about that. All divided by 2 times 1/2 G. 2 times 1/2 is just 1, and you're left with just G. Okay, and again, you know what G is, so all we have to do is plug this stuff in, and you'll get time 2. So now you know the time that the two rocks hit the ground, the important factor to also keep in mind is it says, it's hard to see, but he waits, that's incredibly too much, 0.8 seconds, and then starts to throw the second rock. So it's important that you understand that this time is from when he throws the rock to when it hits the ground. You're going to want to consider that 0.8 seconds that passed that he did not throw the rock, because that will actually give rock number one a little bit of a head start. So the real question is, if you look at T2, is T2 bigger than T1 by 0.8 seconds? Or another way to think about this usefully, T2, I guess I shouldn't call this T2, I'll call it T2 prime, is equal to T2 plus the 0.8 or 0.6, whatever it was, seconds, 0.8 seconds. So T prime is the time it takes rock 2 to hit the ground right after he throws rock 1, which is what we're interested in. And then you just compare T prime 2 with T1 and find out which one's bigger. All you have to do is plug these in your calculator, and keep in mind with this as well, G's still negative, so that turns positive, right? Because G is negative 9.81, and what I did is I just put the negative out front. We did that up here as well. And this is really what you're comparing. So then you'll know which one lands first, and I think from there it won't be too hard to see which one lands quicker by how much. So hopefully that helps out. This was a one-dimensional kinematics problem. We had constant acceleration from gravity, so it's okay to use kinematics. We used y final equals y initial plus v naught t plus 1/2 at squared, where acceleration is just gravity. And that's because it relates everything we know with one thing we don't know, which is t. Now, the only thing that was a little tricky here is we end up with a quadratic equation, but we know how to solve them. Factoring it would be kind of tedious because the numbers aren't going to be clean because of the 1/2 g. I guess you could try, but I just used the quadratic. And we received time 1. And then we followed the exact same process with different numbers to get time 2. And then what we did is we accounted for the fact that he waited 0.8 seconds before he actually threw the ball in the air. And then we're just going to compare the two times to see which one goes first. I hope this helps. The student seemed like they were having a hard time. Oh, and also the coordinate system was important. We're letting up be positive. We're letting right be positive, even though it's not necessary. And we're setting our origin to be right below the man, which is where the rock lands. And we do that because the reason we do this is twofold. So first off, we know the bottom is going to be 0. So we know that y final, that basically gives us y final. That gives us y final. But in addition to that, we know from the ground, which is what we're letting our reference frame be, the top of the building is only 7 meters up, I think. I hope it was 7 meters. Yeah, 7 meters off the ground. So we also know y initial. Same thing here. That's why we set up the coordinate system the way we did, because it's going to give us our y positions pretty easily. If we let our coordinate system be, I don't know, over here, let's say on the other side of the roof, that's kind of silly, isn't it? I mean, I guess actually that would work okay, because you know this is now going to be -7. And I guess because you're not working in the x direction, that's okay. But here's a better example. Let's say you let your coordinate system be, I don't know, here. let's say you let this be positive and this be positive right here in this dot, where this dot is. Well, how does this relate to where the man is? How does it relate to where the ground is? It's kind of silly, and it'll make the problem unnecessarily difficult. So we set the coordinate origin at the very bottom. You could have set it where the man is standing as well, but we just went ahead and set it at the bottom. So hopefully that makes sense.